In this video we'll explore volume. Now, volume is the amount of space a solid occupies. And like area, we can use the moving additivity principles to help us find the volume of shapes that may be more complex. Also, we have the concept of Cavalier's principle about volume, which says that a solid shape that's been sheared is going to have the same volume as the original shape. Now, what that's talking about, the shearing concept, is what happens with oblique solids. It's that idea that we've shifted one of those bases, but we've maintained height. So as long as the height is still the same, the volume of the right cylinder in this case would be the same as the volume of the oblique cylinder, but the height must be maintained. And if we think about it, say we have a stack of pennies, and there's 10 pennies in my stack. So I can see that makes a cylinder. But I also have to remember those are individual pennies. So if I shift them and I make the shape, say, on the right, it looks different, but because each of the individual pieces still have the same volume, I'll still have the same volume as if the pennies have been stacked straight up like a cylinder. And that's also why Cavalier's principle uses that concept of additivity, because it's the volume of those small pieces that makes up the entire. Now, common formulas you should know. For a prism or cylinder, the volume is the area of the base times the height. For a pyramid, it's 1/3 times the area of the base times the height. And for a sphere, it's 4/3 pi r cubed. Now, let's just put together what that means. If you find a formula sheet, normally you find specific formulas for these shapes. So for a cylinder, we know the base is a circle. We know that we said for a prism that the volume is the area of the base times the height. Our base is a circle, and the area of a circle is pi r squared. So you'll find pi r squared h as the common formula for a cylinder. With a square pyramid, we know the base is a square. We know the formula in general is 1/3 times the area of the base times the height. Well, the area of a square would be, in this case, s times s, length times width. So we could say the volume of a square pyramid is 1/3 s squared h. Now let's look at the pyramid in a specific example. We know the Great Pyramid of Giza has a square base of 756 feet and a lateral distance of about 591.5 feet. And I want to know what's the volume of the Great Pyramid. Now, first we have to label what we know. We know the bases and we know the lateral distance. Okay, lateral distance is right here. It's that slant height. Now, what we don't know is the actual height, because height's in the dead center of our pyramid for a square pyramid like this. So we know it's in the center, but we also know it's perpendicular. See, that's marked there. That means if we connect it to the edge, we have a right triangle. Now, knowing that it's in the dead center, we know this little leg has to be half the length of the base, because if I drew it all the way across, it'd have to be the entire length of the base. So if this is 756 feet, I know this has to be 378 feet. And now I have a right triangle. So I can use Pythagorean theorem and plug in the parts I have where the lateral distance, or that slant height, is the hypotenuse. And I'm going to get that my height is about 455 feet. Now I plug in my volume. I know it's 1/3 times the area of the square times the height. So I'm looking at 1/3 of the length times width, so 756 times 756 times the actual height of my pyramid, which is 455 feet. And I'm going to get that the volume is about 86,682,960 cubic feet.